let's look at integral powers / multiples of an element of a group. So here we have seen many groups. We have seen the 12-hour clock group. We have seen the symmetries of an equilateral triangle group. We have seen the permutation of three numbers, addition modulo 4 congruence classes group, and we have seen the group of cube roots of unity. Now let's see how powers and multiples of an element behave inside a group. So let's take a group G under a group operation, and let's say A is in G, an element. Now if G is cyclic and A is the generator, then every element of G can be written as a to the power of n, where n is in the set of integers. If non-cyclic, there is no such generator. So, which means if it is cyclic and A is the generator, we can write the elements as A, comma A times A, comma A times A times A, comma, and so on. And each of these would be in the group. Now, if it is non-cyclic, we will still be able to form powers of an element. The only thing is, those powers will not be able to generate the entire set of elements of the group. So, which means this can be written as a, comma a square, comma a cube, and so on, or in general, a to the power of n. Now here, if n is in the set of integers, then a to the power of n is in G. Now, how about additive groups? Here it is very clearly, we are writing it in multiplicative form. So we are looking at a multiplicative group. Now, if it is a additive group, we would write it like this: a, comma a plus a, comma a plus a plus a, and so on. And each of these would be in G. In short, we can write it as a, comma 2a, comma 3a, and so on. So that in general, it becomes n times a is in G. So this forms the closure property in both multiplicative and additive groups. Multiple elements can be operated in any manner to get an element of G. And if we are writing it this form, then these elements would again be either powers or multiples of an element. So that would be associative property. If n is equal to 0, what happens? Then, since we are talking of a to the power of n, we would end up with a to the power of 0 in case of multiplicative form, or we would end up with 0 times a. And in both these two cases, we would have the identity, which is represented either as E or as I. Now, if n is in the set of negative integers, then a to the power of minus n is equal to, this can be written as a to the power of n to the power of minus 1. That would also be in G. Or in additive form, we would write it as minus n times a. So we separate out minus as minus 1 times n times a. So which can be written as minus and within brackets n times a. And that would also be in G. So that shows existence of inverse, both in multiplicative form and in the additive form. We have seen closure property, associative property, existence of identity, and existence of inverse. Now we have laws of indices or laws of exponents. So for all a in G and m and n in the set of integers, a to the power of m times a to the power of n is equal to a to the power of m plus n, and a to the power of m to the power of n is equal to a to the power of m times n. So that was laws of indices. Now laws of multiples. For all a in G and m and n in the set of integers, we have m times a plus n times a is equal to m plus n times a. And we have n times m times a is equal to n times m times a. Here, this is applicable only in abelian groups. Now here remember, if we are talking of a and a square, they are commutative. But when we want to add them up, then we require commutativity. So this is applicable only in abelian groups. So that was integral powers and multiples of an element of a group in multiplicative and additive groups. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.